Hi, the section 5.3, the rate models. So this is a little off the main topic of chapter 5. So here's the idea. So often we want to fit a regression model for the ratio, the y over z. So log of the y over z is equal to the x beta. So if y and z are the positive numbers, then the log of y over z ranges from negative infinity to positive infinity. So this link, the log link, that works better if the x beta also ranges from negative infinity to positive infinity. But in this regression model, sometimes still we want to keep the left-hand side as the log of y. So for example, we may want to compare the residual sum of squares with this regression model with another model. The log of y is equal to x times some parameter gamma. So in this case, for example, if log of y is equal to the log of z plus x beta, so mathematically these two models are the same, but both models, so this model and this model, both models have the same response variable, so it's easier to compare, for example, the sum of squared residuals. And actually the R has some function to keep this shape, so response, so log of y as response. So we can actually fit this model. So note that this log of z does not have any coefficient, and only x has coefficient. So this is known as a rate model. Yeah, and possibly the model has some error term. So if the model is, for example, the binomial, logistic model, then we don't have an error term, but the usual linear model, that we have x beta plus epsilon. So possibly there is error term on the right-hand side. And so here is the example. So this example is for the proportion of abnormal cells by the gamma radiation. So basically the response variable is here. So Ca over cells. So Ca is abnormal cells and cells is the total number of cells. So it makes more sense scientifically to consider the Ca over the cells, and the two level of radiation. So this is dose amount and the dose rate. So these are possible the predictors. So these are possible x, and this is basically ratio should be y. So we fit the log of Ca over cells is equal to this variable, and actually the dose amount and the dose rate are both discrete variable, and it sounds the dose amount is more useful. So we use the factor variable, the dose amount, plus maybe this is a kind of the ANOVA model, and the ice factor, the plus the epsilon ij or something like that. So this is the model we want to fit. So we have the parameter beta. So maybe the beta I. So actually those amount have the 3 levels. So that we have the several parameters. Maybe I should say the intercept plus this one. And actually this is I is equal to the 2 to 3. So I is equal to 1 is the baseline. So we want to fit the model, but we actually want to use the log of Ca as y. So log of Ca is equal to log of cells plus this the beta naught plus the beta 1, beta I, the dose amount. So this. So we want to fit this model. And we just want to compare this model with another model which have also some parameter for the log of cells. So first one is the usual linear regression. So log of CA on log of cells plus those amount as factor. And the textbook uses the Poisson, the regression model for this question, but the log of CA is not the count anymore. So it can be negative and also it's fractional. So it does not seem appropriate to fit the Poisson model here. And also the binomial model, it does not sound appropriate. So I used just linear regression. So GLM without any option is linear regression. So I use linear regression. And actually, if you fit the parameter for log of cells, it's close to 1. So if we see the standard error, you can see this is close to 1. But still, it's estimated, and the 0.96 is the best to minimize the sum of squared residuals. And those amount have 3 levels, the 1, 2.5, and 5. So 1 is the baseline, and we have the 2 more parameters. And you can see standard error and the t-values here, 6 and 5.6.3, 5.7, and 7.5. So all very significant. So how about the rate model if we fix log of cells? Then estimation result is here. So the offset log of cells, then parameter is always 1. Then we have the 2 variables, those amount level 2.5 and 5. Then estimate is here, 1.64 and 2.78. So these are kind of similar, 1.58 and 2.70 before. And the standard deviation, and actually standard deviation gets much smaller and the t-values are more significant. So 12 and 21. So previously 5.7 and 7.5. So you can easily imagine that if the data is worse, then the offset model, so the rate model, gets more variable significant. And of course, if we don't put the offset function, then we can optimize that parameter also, so error gets smaller. But this is a kind of the interpretation issue. So it's more natural to think about the CA over cells. So if we if we put that assumption, then we can show that the sum coefficients are more statistically significant. So it's logically the more solid model.